A hypothesis test can be regarded as either a judgment of a hypothesis or as a judgment of evidence. Philosopher's beans. The following example was produced by a philosopher describing scientific methods generations before hypothesis testing was formalized and popularized. 55. Few beans of this handful are white. Most beans in this bag are white. Therefore, probably, these beans were taken from another bag. This is an hypothetical inference. The beans in the bag are the population. The handful are the sample. The null hypothesis is that the sample originated from the population. The criterion for rejecting the null hypothesis is a obvious difference in appearance and informal difference in the mean. The interesting result is that consideration of a real population and a real sample produced an imaginary bag. The philosopher was considering logic rather than probability. To be a real statistical hypothesis test, this example requires the formalities of a probability calculation and a comparison of that probability to a standard. A simple generalization of the example considers a mixed bag of beans and a handful that contain either very few or very many white beans. The generalization considers both extremes. It requires more calculations and more comparisons to arrive at a formal answer, but the core philosophy is unchanged. If the composition of the handful is greatly different from that of the bag, then the sample probably originated from another bag. The original example is termed a one-sided or a one-tailed test, while the generalization is termed a two-sided or two-tailed test. The statement also relies on the inference that the sampling was random. If someone had been picking through the bag to find white beans, then it would explain why the handful had so many white beans, and also explain why the number of white beans in the bag was depleted, although the bag is probably intended to be assumed much larger than one's hand. Clairvoyant card game. A person, the subject, is tested for clairvoyance. They are shown the back face of a randomly chosen playing card 25 times and asked which of the four suits it belongs to. The number of hits, or correct answers, is called X. As we try to find evidence of their clairvoyance, for the time being the null hypothesis is that the person is not clairvoyant. 56. The alternative is, the person is more or less clairvoyant. If the null hypothesis is valid, the only thing the test person can do is guess. For every card, the probability, relative frequency, of any single suit appearing is 1/4. If the alternative is valid, the test subject will predict the suit correctly with probability greater than 1/4. We will call the probability of guessing correctly P. The hypotheses, then, are null hypothesis, just guessing, and alternative hypothesis, true clairvoyant. When the test subject correctly predicts all 25 cards, we will consider them clairvoyant, and reject the null hypothesis. Thus also with 24 or 23 hits. With only 5 or 6 hits, on the other hand, there is no cause to consider them so. But what about 12 hits, or 17 hits? What is the critical number, C, of hits, at which point we consider the subject to be clairvoyant? How do we determine the critical value C? With the choice C equals 25, i.e. we only accept clairvoyance when all cards are predicted correctly, we're more critical than with C equals 10. In the first case almost no test subjects will be recognized to be clairvoyant, in the second case, a certain number will pass the test. In practice, one decides how critical one will be. That is, one decides how often one accepts an error of the first kind, a false positive, or type 1 error. With C equals 25 the probability of such an error is, and hence, very small. The probability of a false positive is the probability of randomly guessing correctly all 25 times. Being less critical, with C equals 10, gives dot. Thus, C equals 10 yields a much greater probability of false positive. Before the test is actually performed, the maximum acceptable probability of a type 1 error, alpha, is determined. Typically, values in the range of 1% to 5% are selected. If the maximum acceptable error rate is 0, an infinite number of correct guesses is required. Depending on this type 1 error rate, the critical value C is calculated. For example, if we select an error rate of 1%, C is calculated thus. Dot. From all the numbers C, with this property, we choose the smallest, in order to minimize the probability of a type 2 error, a false negative. For the above example, we select variations and subclasses. Statistical hypothesis testing is a key technique of both frequentist inference and Bayesian inference, although the two types of inference have notable differences. Statistical hypothesis tests define a procedure that fixes, the probability of incorrectly deciding that a default position, null hypothesis, is incorrect. The procedure is based on how likely it would be for a set of observations to occur if the null hypothesis were true. This probability of making an incorrect decision is not the probability that the null hypothesis is true, nor whether any specific alternative hypothesis is true. This contrasts with other possible techniques of decision theory in which the null and alternative hypothesis are treated on a more equal basis. One naive Bayesian approach to hypothesis testing is to base decisions on the posterior probability, 57-58, but this fails when comparing point and continuous hypotheses. Other approaches to decision-making, such as Bayesian decision theory, attempt to balance the consequences of incorrect decisions across all possibilities, rather than concentrating on a single null hypothesis. A number of other approaches to reaching a decision based on data are available via decision theory and optimal decisions, some of which have desirable properties. Hypothesis testing, though, is a dominant approach to data analysis in many fields of science. Extensions to the theory of hypothesis testing include the study of the power of tests, i.e. the probability of correctly rejecting the null hypothesis given that it is false. Such considerations can be used for the purpose of sample size determination prior to the collection of data. Neyman-Pearson hypothesis testing. An example of Neyman-Pearson hypothesis testing, or null hypothesis statistical significance testing, can be made by a change to the radioactive suitcase example. If the suitcase is actually a shielded container for the transportation of radioactive material, then a test might be used to select among 3 hypotheses. No radioactive source present, 1 present, 2 all present. The test could be required for safety, with actions required in each case. The Neyman-Pearson lemma of hypothesis testing says that a good criterion for the selection of hypotheses is the ratio of their probabilities, a likelihood ratio. A simple method of solution is to select the hypothesis with the highest probability for the Geiger counts observed. The typical result matches intuition. Few counts imply no source, many counts imply 2 sources, and intermediate counts imply 1 source. Notice also that usually there are problems for proving a negative. Null hypotheses should be at least falsifiable. Neyman-Pearson theory can accommodate both prior probabilities and the costs of actions resulting from decisions. 59. The former allows each test to consider the results of earlier tests, unlike Fisher's significance tests. The latter allows the consideration of economic issues, for example, as well as probabilities. A likelihood ratio remains a good criterion for selecting among hypotheses. The 2 forms of hypothesis testing are based on different problem formulations. The original test is analogous to a true-false question. The Neyman-Pearson test is more like multiple choice. In the view of Tukey, 60, the former produces a conclusion on the basis of only strong evidence while the latter produces a decision on the basis of available evidence. While the 2 tests seem quite different both mathematically and philosophically, later developments lead to the opposite claim. Consider many tiny radioactive sources. The hypotheses become 0, 1, 2, 3 grains of radioactive sand. There is little distinction between none or some radiation Fisher, and 0 grains of radioactive sand versus all of the alternatives, Neyman-Pearson. The major Neyman-Pearson paper of 1933-11 also considered composite hypotheses, ones whose distribution includes an unknown parameter. An example proved the optimality of the student's t-test. There can be no better test for the hypothesis under consideration, p. 321. Neyman-Pearson theory was proving the optimality of Fisherian methods from its inception. Fisher's significance testing has proven a popular flexible statistical tool in application with little mathematical growth potential. Neyman-Pearson hypothesis testing is claimed as a pillar of mathematical statistics, 61, creating a new paradigm for the field. It also stimulated new applications in statistical process control, detection theory, decision theory, and game theory. Both formulations have been successful, but the successes have been of a different character. The dispute over formulations is unresolved. Science primarily uses Fisher's slightly modified formulation as taught in introductory statistics. Statisticians study Neyman-Pearson theory in graduate school. Mathematicians are proud of uniting the formulations. Philosophers consider them separately. Learned opinions deem the formulations variously competitive. Fisher versus Neyman, incompatible. 9, are complementary. 13. The dispute has become more complex since Bayesian inference has achieved respectability. The terminology is inconsistent. Hypothesis testing can mean any mixture of 2 formulations that both change with time. Any discussion of significance testing versus hypothesis testing is doubly vulnerable to confusion. Fisher thought that hypothesis testing was a useful strategy for performing industrial quality control. However, he strongly disagreed that hypothesis testing could be useful for scientists. 10. Hypothesis testing provides a means of finding test statistics used in significance testing. 13. The concept of power is useful in explaining the consequences of adjusting the significance level and is heavily used in sample size determination. The 2 methods remain philosophically distinct. 15. They usually, but not always, produce the same mathematical answer. The preferred answer is context dependent. 13. While the existing merger of Fisher and Neyman-Pearson theories has been heavily criticized, modifying the merger to achieve Bayesian goals has been considered. 62. Criticism. Criticism of statistical hypothesis testing fills volumes. 63, 64, 65, 66, 67, 68. Much of the criticism can be summarized by the following issues. The interpretation of a p-value is dependent upon stopping rule and definition of multiple comparison. The former often changes during the course of a study and the latter is unavoidably ambiguous. The former often changes during the course of a study and the latter is unavoidably ambiguous. i.e., p-values depend on both the data observed and on the other possible data that might have been observed but weren't. 69. Confusion resulting, in part, from combining the methods of Fisher and Neyman-Pearson which are conceptually distinct. 60. Emphasis on statistical significance to the exclusion of estimation and confirmation by repeated experiments. 70. Rigidly requiring statistical significance as a criterion for publication, resulting in publication bias. 71. Most of the criticism is indirect. Rather than being wrong, statistical hypothesis testing is misunderstood, overused and misused. When used to detect whether a difference exists between groups, a paradox arises. As improvements are made to experimental design, e.g. increased precision of measurement and sample size, the test becomes more lenient. Unless one accepts the absurd assumption that all sources of noise in the data cancel out completely, the chance of finding statistical significance in either direction approaches 100%. 72. However, this absurd assumption that the mean difference between 2 groups cannot be 0 implies that the data cannot be independent and identically distributed I.D. Because the expected difference between any 2 subgroups of I.D. random variance is 0, therefore, the I.D. assumption is also absurd. Layers of philosophical concerns. The probability of statistical significance is a function of decisions made by experimenters, analysts. 73. If the decisions are based on convention they are termed arbitrary or mindless. 74. While those not so based may be termed subjective. To minimize type 2 errors, large samples are recommended. In psychology practically all null hypotheses are claimed to be false for sufficiently large samples so, it is usually nonsensical to perform an experiment with the sole aim of rejecting the null hypothesis. 75. Statistically significant findings are often misleading, in psychology. 76. Statistical significance does not imply practical significance, and correlation does not imply causation. Casting doubt on the null hypothesis is thus far from directly supporting the research hypothesis. IT does not tell us what we want to know. 77. Lists of dozens of complaints are available. 67, 78, 79. Critics and supporters are largely in factual agreement regarding the characteristics of null hypothesis significance testing, NHST. While it can provide critical information, it is inadequate as the sole tool for statistical analysis. Successfully rejecting the null hypothesis may offer no support for the research hypothesis. The continuing controversy concerns the selection of the best statistical practices for the near-term future given the existing practices. However, adequate research design can minimize this issue. Critics would prefer to ban NHST completely, forcing a complete departure from those practices, 80, while supporters suggest a less absolute change. Controversy over significance testing, and its effects on publication bias in particular, has produced several results. The American Psychological Association has strengthened its statistical reporting requirements after review. 81. Medical journal publishers have recognized the obligation to publish some results that are not statistically significant to combat publication bias. 82. And a journal of articles in support of the null hypothesis, has been created to publish such results exclusively. 83. Textbooks have added some cautions. 84. And increased coverage of the tools necessary to estimate the size of the sample required to produce significant results. Few major organizations have abandoned use of significance tests, although some have discussed doing so. 81. For instance, in 2023, the editors of the Journal of Physiology strongly recommend the use of estimation methods for those publishing in the journal, meaning the magnitude of the effect size, to allow readers to judge whether a finding has practical, physiological, or clinical relevance, and confidence intervals to convey the precision of that estimate, saying, ultimately, it is the physiological importance of the data that those publishing in the Journal of Physiology should be most concerned with, rather than the statistical significance. 85. Alternatives. A unifying position of critics is that statistics should not lead to an accept-reject conclusion or decision, but to an estimated value with an interval estimate. This data analysis philosophy is broadly referred to as estimation statistics. Estimation statistics can be accomplished with either frequentist, 1, or Bayesian methods. 86, 87. Critics of significance testing have advocated basing inference less on p-values and more on confidence intervals for effect sizes for importance, prediction intervals for confidence, replications and extensions for replicability, meta-analyses for generality. 88. But none of these suggested alternatives inherently produces a decision. Layman said that hypothesis testing theory can be presented in terms of conclusions, decisions, probabilities, or confidence intervals. The distinction between the approaches is largely one of reporting and interpretation. 25. Bayesian inference is one proposed alternative to significance testing. Nickerson cited 10 sources suggesting it, including Rosenboom, 1960. 78. For example, Bayesian parameter estimation can provide rich information about the data from which researchers can draw inferences, while using uncertain priors that exert only minimal influence on the results when enough data is available. Psychologist John K. Kruschke has suggested Bayesian estimation is an alternative for the t-test, 86, and has also contrasted Bayesian estimation for assessing null values with Bayesian model comparison for hypothesis testing. 87. Two competing models, hypotheses can be compared using Bayes factors. 89. Bayesian methods could be criticized for requiring information that is seldom available in the cases where significance testing is most heavily used. Neither the prior probabilities nor the probability distribution of the test statistic under the alternative hypothesis are often available in the social sciences. 78. Advocates of a Bayesian approach sometimes claim that the goal of a researcher is most often to objectively assess the probability that a hypothesis is true based on the data they have collected. 90. 91. Neither Fisher's significance testing, nor Neyman-Pearson hypothesis testing can provide this information, and do not claim to. The probability a hypothesis is true can only be derived from use of Bayes' theorem, which was unsatisfactory to both the Fisher and Neyman-Pearson camps due to the explicit use of subjectivity in the form of the prior probability. 11. 92. Fisher's strategy is to sidestep this with the p-value, an objective index based on the data alone, followed by inductive inference, while Neyman-Pearson devised their approach of inductive behavior. Null hypothesis. In scientific research, the null hypothesis, often denoted H0, is the claim that the effect being studied does not exist. Note 1. The null hypothesis can also be described as a hypothesis in which no relationship exists between two sets of data or variables being analyzed. If the null hypothesis is true, any experimentally observed effect is due to chance alone, hence the term null. In contrast with the null hypothesis, an alternative hypothesis is developed, which claims that a relationship does exist between two variables. Basic definitions. The null hypothesis and the alternative hypothesis are types of conjectures used in statistical tests to make statistical inferences, which are formal methods of reaching conclusions and separating scientific claims from statistical noise. The statement being tested in a test of statistical significance is called the null hypothesis. The test of significance is designed to assess the strength of the evidence against the null hypothesis, or a statement of no effect, or no difference. 2. It is often symbolized as H0. The statement that is being tested against the null hypothesis is the alternative hypothesis. 2. Symbols may include H1 and HA. A statistical significance test starts with a random sample from a population. If the sample data are consistent with the null hypothesis, then you do not reject the null hypothesis. If the sample data are inconsistent with the null hypothesis, then you reject the null hypothesis and conclude that the alternative hypothesis is true. 3. Consider the following example. Given the test scores of two random samples, one of men and one of women, does one group score better than the other? A possible null hypothesis is that the mean male score is the same as the mean female score. H0, mu1 equals mu2 where H0 equals the null hypothesis. Mu1 equals the mean of population 1, and mu2 equals the mean of population 2. A stronger null hypothesis is that the two samples have equal variances in shapes of their respective distributions. Terminology. Simple hypothesis. Any hypothesis which specifies the population distribution completely. For such a hypothesis, the sampling distribution of any statistic is a function of the sample size alone. Composite hypothesis. Any hypothesis which does not specify the population distribution completely. For example, a hypothesis specifying a normal distribution with a specified mean and an unspecified variance. The simple composite distinction was made by Neyman and Pearson. 5. Exact hypothesis. Any hypothesis that specifies an exact parameter value. 4. Composite hypothesis. Any hypothesis. Simple hypothesis. Any hypothesis which specifies the population distribution completely. For such a hypothesis, the sampling distribution of any statistic is a function of the sample size alone. Composite hypothesis. Any hypothesis which does not specify the population distribution completely. For example, a hypothesis specifying a normal distribution with a specified mean and an unspecified variance. The simple composite distinction was made by Neyman and Pearson. 5. Exact hypothesis. Any hypothesis that specifies an exact parameter value. 6. Example, mu equals 100. Synonym, point. Hypothesis. Inexact hypothesis. Those specifying a parameter range or interval. Examples, mu is less than or equal to 100, 95 is less than or equal to mu is less than or equal to 105. Fisher required an exact null hypothesis for testing, see the quotations below. A one-tailed hypothesis tested using a one-sided test. 2 is an inexact hypothesis in which a value of a parameter is specified as being either above or equal to a certain value, or below or equal to a certain value. A one-tailed hypothesis is said to have directionality. Any hypothesis which specifies the population distribution completely. For such a hypothesis, the sampling distribution of any statistic is a function of the sample size alone. Composite hypothesis. Any hypothesis which does not specify the population distribution completely. For example, a hypothesis specifying a normal distribution with a specified mean and an unspecified variance. The simple composite distinction was made by Neyman and Pearson. 5. Exact hypothesis. Any hypothesis that specifies an exact parameter value. 6. Example, mu equals 100. Synonym, point. Hypothesis. Inexact hypothesis. Those specifying a parameter range or interval. Examples, mu is less than or equal to 100, 95 is less than or equal to mu is less than or equal to 105. Fisher required an exact null hypothesis for testing, see the quotations below. A one-tailed hypothesis tested using a one-sided test. 2 is an inexact hypothesis in which a value of a parameter is specified as being either above or equal to a certain value, or below or equal to a certain value. A one-tailed hypothesis is said to have directionality. Fisher's original lady tasting tea example was a one-tailed test. The null hypothesis was asymmetric. The probability of guessing all cups correctly was the same as guessing all cups incorrectly, but Fisher noted that only guessing correctly was compatible with the lady's claim. Technical description. The null hypothesis is a default hypothesis that a quantity to be measured is zero null. Typically, the quantity to be measured is the difference between two situations. For instance, trying to determine if there is a positive proof that an effect has occurred or that samples derive from different batches. 7, 8. The null hypothesis is generally assumed to remain possibly true. Multiple analyses can be performed to show how the hypothesis should either be rejected or excluded, e.g. having a high confidence level, thus demonstrating a statistically significant difference. This is demonstrated by showing that 0 is outside of the specified confidence interval of the measurement on either side, typically within the real numbers. 8. Failure to exclude the null hypothesis with any confidence does not logically confirm or support the unprovable null hypothesis. When it is proven that something is e.g. bigger than x, it does not necessarily imply it is plausible that it is smaller or equal than x, it may instead be a poor quality measurement with low accuracy. Confirming the null hypothesis two-sided would amount to positively proving it is bigger or equal than 0 and to positively proving it is smaller or equal than 0. This is something for which infinite accuracy is needed as well as exactly zero effect, neither of which normally are realistic. Also, measurements will never indicate a non-zero probability of exactly zero difference. So failure of an exclusion of a null hypothesis amounts to a don't know at the specified confidence level. It does not immediately imply null somehow, as the data may already show a less strong indication for a non-null. The used confidence level does absolutely certainly not correspond to the likelihood of null at failing to exclude. In fact, in this case, a high used confidence level expands the still plausible range. A non-null hypothesis can have the following meanings, depending on the author: a value other than 0 is used, b some margin other than 0 is used, and c the alternative hypothesis. 9, 10. Testing, excluding or failing to exclude the null hypothesis provides evidence that there are or are not statistically sufficient grounds to believe there is a relationship between two phenomena, e.g., that a potential treatment has a non-zero effect, either way. Testing the null hypothesis is a central task in statistical hypothesis testing in the modern practice of science. There are precise criteria for excluding or not excluding a null hypothesis at a certain confidence level. The confidence level should indicate the likelihood that much more and better data would still be able to exclude the null hypothesis on the same side. 8. The concept of a null hypothesis is used differently in two approaches to statistical inference. In the significance testing approach of Ronald Fisher, a null hypothesis is rejected if the observed data are significantly unlikely to have occurred if the null hypothesis were true. In this case, the null hypothesis is rejected and an alternative hypothesis is accepted in its place. If the data are consistent with the null hypothesis statistically possibly true, then the null hypothesis is not rejected. In neither case is the null hypothesis or its alternative proven. With better or more data, the null may still be rejected. This is analogous to the legal principle of presumption of innocence, in which a suspect or defendant is assumed to be innocent. Null is not rejected until proven guilty. Null is rejected beyond a reasonable doubt to a statistically significant degree. 8. In the hypothesis testing approach of Jerzy Neyman and Egan Pearson, a null hypothesis is contrasted with an alternative hypothesis, and the two hypotheses are distinguished on the basis of data, with certain error rates. It is used in formulating answers in research. Statistical inference can be done without a null hypothesis, by specifying a statistical model corresponding to each candidate hypothesis, and by using model selection techniques to choose the most appropriate model. 11. The most common selection techniques are based on either a Kaika information criterion or Bayes factor. Principle. Hypothesis testing requires constructing a statistical model of what the data would look like if chance or random processes alone were responsible for the results. The hypothesis that chance alone is responsible for the results is called the null hypothesis. The model of the result of the random process is called the distribution under the null hypothesis. The obtained results are compared with the distribution under the null hypothesis, and the likelihood of finding the obtained results is thereby determined. 12. Hypothesis testing works by collecting data and measuring how likely the particular set of data is, assuming the null hypothesis is true when the study is on a randomly selected representative sample. The null hypothesis assumes no relationship between variables in the population from which a sample is selected. 13. If the dataset of a randomly selected representative sample is very unlikely relative to the null hypothesis defined as being part of a class of sets of data that only rarely will be observed, the experimenter rejects the null hypothesis, concluding it probably is false. This class of datasets is usually specified via a test statistic, which is designed to measure the extent of apparent departure from the null hypothesis. The procedure works by assessing whether the observed departure, measured by the test statistic, is larger than a value defined, so that the probability of occurrence of a more extreme value is small under the null hypothesis, usually in less than either 5% or 1% of similar datasets in which the null hypothesis does hold. If the data do not contradict the null hypothesis, then only a weak conclusion can be made, namely, that the observed dataset provides insufficient evidence against the null hypothesis. In this case, because the null hypothesis could be true or false, in some contexts this is interpreted as meaning that the data give insufficient evidence to make any conclusion, while in other contexts, it is interpreted as meaning that there is not sufficient evidence to support changing from a currently useful regime to a different one. Nevertheless, if at this point the effect appears likely and/or large enough, there may be an incentive to further investigate, such as running a bigger sample. For instance, a certain drug may reduce the risk of having a heart attack. Possible null hypotheses are, this drug does not reduce the risk of having a heart attack, or, this drug has no effect on the risk of having a heart attack. The test of the hypothesis consists of administering the drug to half of the people in a study group as a controlled experiment. If the data show a statistically significant change in the people receiving the drug, the null hypothesis is rejected. Goals of null hypothesis tests. There are many types of significance tests for one, two or more samples, for means, variances in proportions, paired or unpaired data, for different distributions, for large and small samples, all have null hypotheses. There are also at least 4 goals of null hypotheses for significance tests. 14 technical null hypotheses are used to verify statistical assumptions. For example, the residuals between the data and a statistical model cannot be distinguished from random noise. If true, there is no justification for complicating the model. Scientific null assumptions are used to directly advance a theory. For example, the angular momentum of the universe is 0. If not true, the theory of the early universe may need revision. Null hypotheses of homogeneity are used to verify that multiple experiments are producing consistent results. For example, the effect of a medication on the elderly is consistent with that of the general adult population. If true, this strengthens the general effectiveness conclusion and simplifies recommendations for use. Null hypotheses that assert the equality of effect of 2 or more alternative treatments, for example, a drug and a placebo, are used to reduce scientific claims based on statistical noise. This is the most popular null hypothesis. It is so popular that many statements about significant testing assume such null hypotheses. Rejection of the null hypothesis is not necessarily the real goal of a significance tester. An adequate statistical model may be associated with a failure to reject the null. The model is adjusted until the null is not rejected. The numerous uses of significance testing were well known to Fisher, who discussed many in his book written a decade before defining the null hypothesis. 15. A statistical significance test shares much mathematics with a confidence interval. They are mutually illuminating. A result is often significant when there is confidence in the sign of a relationship. The interval does not include 0. Whenever the sign of a relationship is important, statistical significance is a worthy goal. This also reveals weaknesses of significance testing. A result can be significant without a good estimate of the strength of a relationship. Significance can be a modest goal. A weak relationship can also achieve significance with enough data. Reporting both significance and confidence intervals is commonly recommended. The varied uses of significance tests reduce the number of generalizations that can be made about all applications. Choice of the null hypothesis. The choice of the null hypothesis is associated with sparse and inconsistent advice. Fisher mentioned few constraints on the choice and stated that many null hypotheses should be considered and that many tests are possible for each. The variety of applications and the diversity of goals suggests that the choice can be complicated. In many applications, the formulation of the test is traditional. A familiarity with the range of tests available may suggest a particular null hypothesis and test. Formulating the null hypothesis is not automated, though the calculations of significance testing usually are. David Cox said, "How the translation from subject matter problem to statistical model is done is often the most critical part of an analysis." 16. A statistical significance test is intended to test a hypothesis. If the hypothesis summarizes a set of data, there is no value in testing the hypothesis on that set of data. Example, if a study of last year's weather reports indicates that rain in a region falls primarily on weekends, it is only valid to test that null hypothesis on weather reports from any other year. Testing hypotheses suggested by the data is circular reasoning that proves nothing. It is a special limitation on the choice of the null hypothesis. A routine procedure is as follows: start from the scientific hypothesis. Translate this to a statistical alternative hypothesis and proceed. Because HA expresses the effect that we wish to find evidence for, we often begin with HA and then set up H0 as the statement that the hoped for effect is not present. 2. This advice is reversed for modeling applications where we hope not to find evidence against the null. A complex case example is as follows. 17. The gold standard in clinical research is the randomized placebo-controlled double-blind clinical trial. But testing a new drug against a medically ineffective placebo may be unethical for a serious illness. Testing a new drug against an older medically effective drug raises fundamental philosophical issues regarding the goal of the test and the motivation of the experimenters. The standard, no difference, null hypothesis may reward the pharmaceutical company for gathering inadequate data. Difference is a better null hypothesis in this case, but statistical significance is not an adequate criterion for reaching a nuanced conclusion which requires a good numeric estimate of the drug's effectiveness. A minor, or simple, proposed change in the null hypothesis, new versus old, rather than new versus placebo, can have a dramatic effect on the utility of a test for complex non-statistical reasons. Directionality. The choice of null hypothesis H0 and consideration of directionality C, one-tailed test, is critical. Tailedness of the null hypothesis test. Consider the question of whether a tossed coin is fair, i.e. that on average it lands heads up 50% of the time, and an experiment where you toss the coin 5 times. A possible result of the experiment that we consider here is 5 heads. Let outcomes be considered unlikely with respect to an assumed distribution if their probability is lower than a significance threshold of 0.05. A potential null hypothesis implying a one-tailed test is, this coin is not biased toward heads. Beware that, in this context, the term, one-tailed, does not refer to the outcome of a single coin toss, i.e., whether or not the coin comes up, tails, instead of, heads. The term, one-tailed, refers to a specific way of testing the null hypothesis in which the critical region, also known as, region of rejection, ends up in on only one side of the probability distribution. Indeed, with a fair coin the probability of this experiment outcome is 1/25 equals 0.031, which would be even lower if the coin were biased in favor of tails. Therefore, the observations are not likely enough for the null hypothesis to hold, and the test refutes it. Since the coin is ostensibly neither fair nor biased toward tails, the conclusion of the experiment is that the coin is biased towards heads. Alternatively, a null hypothesis implying a two-tailed test is, this coin is fair. This one null hypothesis could be examined by looking out for either too many tails or too many heads in the experiments. The outcomes that would tend to refute this null hypothesis are those with a large number of heads or a large number of tails, and our experiment with 5 heads would seem to belong to this class. However, the probability of 5 tosses of the same kind, irrespective of whether these are head or tails, is twice as much as that of the 5-head occurrence singly considered. Hence, under this two-tailed null hypothesis, the observation receives a probability value of 0.063. Hence again, with the same significance threshold used for the one-tailed test, 0.05, the same outcome is not statistically significant. Therefore, the two-tailed null hypothesis will be preserved in this case, not supporting the conclusion reached with the single-tailed null hypothesis, that the coin is biased towards heads. This example illustrates that the conclusion reached from a statistical test may depend on the precise formulation of the null and alternative hypotheses. Discussion. Fisher said, the null hypothesis must be exact, that is free of vagueness and ambiguity, because it must supply the basis of the problem of distribution, of which the test of significance is the solution, implying a more restrictive domain for H0. 18. According to this view, the null hypothesis must be numerically exact. It must state that a particular quantity or difference is equal to a particular number. In classical science, it is most typically the statement that there is no effect of a particular treatment. In observations, it is typically that there is no difference between the value of a particular measured variable and that of a prediction. Most statisticians believe that it is valid to state direction as a part of null hypothesis, or as part of a null hypothesis alternative hypothesis pair. 19. However, the results are not a full description of all the results of an experiment, merely a single result tailored to one particular purpose. For example, consider an H0 that claims the population mean for a new treatment is an improvement on a well-established treatment with population mean equals 10, known from long experience, with the one-tailed alternative being that the new treatment's mean greater than 10. If the sample evidence obtained through x bar equals -200 and the corresponding t-test statistic equals -50, the conclusion from the test would be that there is no evidence that the new treatment is better than the existing one. It would not report that it is markedly worse. But that is not what this particular test is looking for. To overcome any possible ambiguity in reporting the result of the test of a null hypothesis, it is best to indicate whether the test was two-sided and, if one-sided, to include the direction of the effect being tested. The statistical theory required to deal with the simple cases of directionality dealt with here, and more complicated ones, makes use of the concept of an unbiased test. The directionality of hypotheses is not always obvious. The explicit null hypothesis of Fisher's lady tasting tea example was that the lady had no such ability, which led to a symmetric probability distribution. The one-tailed nature of the test resulted from the one-tailed alternate hypothesis, a term not used by Fisher. The null hypothesis became implicitly one-tailed. The logical negation of the lady's one-tailed claim was also one-tailed. Claim, ability greater than O, stated null, ability equals 0, implicit null, ability is less than or equal to O. Pure arguments over the use of one-tailed tests are complicated by the variety of tests. Some tests, for instance the chi-2 goodness of fit test, are inherently one-tailed. Some probability distributions are asymmetric. The traditional tests of 3 or more groups are two-tailed. Advice concerning the use of one-tailed hypotheses has been inconsistent and accepted practice varies among fields. 20. The greatest objection to one-tailed hypotheses is their potential subjectivity. A non-significant result can sometimes be converted to a significant result by the use of a one-tailed hypothesis, as a fair coin test, at the whim of the analyst. The flip side of the argument, one-sided tests are less likely to ignore a real effect. One-tailed tests can suppress the publication of data that differs in sign from predictions. Objectivity was a goal of the developers of statistical tests. It is a common practice to use a one-tailed hypothesis by default. However, if you do not have a specific direction firmly in mind in advance, use a two-sided alternative. Moreover, some users of statistics argue that we should always work with the two-sided alternative. 221. One alternative to this advice is to use 3 outcome tests. It eliminates the issues surrounding directionality of hypotheses by testing twice, once in each direction and combining the results to produce 3 possible outcomes. 22. Variations on this approach have a history, being suggested perhaps 10 times since 1950. 23. Disagreements over one-tailed tests flow from the philosophy of science. While Fisher was willing to ignore the unlikely case of the lady guessing all cups of tea incorrectly, which may have been appropriate for the circumstances, medicine believes that a proposed treatment that kills patients is significant in every sense and should be reported and perhaps explained. Poor statistical reporting practices have contributed to disagreements over one-tailed tests. Statistical significance resulting from two-tailed tests is insensitive to the sign of the relationship. Reporting significance alone is inadequate. The treatment has an effect, is the uninformative result of a two-tailed test. The treatment has a beneficial effect, is the more informative result of a one-tailed test. The treatment has an effect, reducing the average length of hospitalization by 1.5 days, is the most informative report, combining a two-tailed significance test result with a numeric estimate of the relationship between treatment and effect. Explicitly reporting a numeric result eliminates the philosophical advantage of a one-tailed test. An underlying issue is the appropriate form of an experimental science without numeric predictive theories. A model of numeric results is more informative than a model of effect signs positive, negative or unknown, which is more informative than a model of simple significance, non-zero or unknown. In the absence of numeric theory, signs may suffice. History of statistical tests. The history of the null and alternative hypotheses has much to do with the history of statistical tests. 24-25. Before 1925, there are occasional transient traces of statistical tests in past centuries, which were early examples of null hypotheses. In the late 19th century, statistical significance was defined. In the early 20th century, important probability distributions were defined. Gossett and Pearson worked on specific cases of significance testing. 1925. Fisher published the first edition of Statistical Methods for Research Workers, which defined the statistical significance test and made it a mainstream method of analysis for much of experimental science. The text was devoid of proofs and weak on explanations, but was filled with real examples. It placed statistical practice in the sciences well in advance of published statistical theory. 1933. In a series of papers published over a decade starting in 1928, Neyman and Pearson defined the statistical hypothesis test as a proposed improvement on Fisher's test. The papers provided much of the terminology for statistical tests, including alternative hypothesis and H0 as a hypothesis to be tested using observational data, with H1, H2 as alternatives. 1935. Fisher published the first edition of the book The Design of Experiments, which introduced the null hypothesis 26 by example rather than by definition, and carefully explained the rationale for significance tests in the context of the interpretation of experimental results. Fisher and Neyman quarreled over the relative merits of their competing formulations until Fisher's death in 1962. Career changes in World War II ended the partnership of Neyman and Pearson. The formulations were merged by relatively anonymous textbook writers, experimenters, journal editors, and mathematical statisticians without input from either Fisher or Neyman. 24. The subject today combines much of the terminology and explanatory power of Neyman and Pearson with the scientific philosophy and calculations provided by Fisher. Whether statistical testing is properly one subject or two remains a source of disagreement. 27. Sample of 2. One text refers to the subject as hypothesis testing, with no mention of significance testing in the index, while another says significance testing, with a section on inference as a decision. Fisher developed significance testing as a flexible tool for researchers to weigh their evidence. Instead, testing has become institutionalized. Statistical significance has become a rigidly defined and enforced criterion for the publication of experimental results in many scientific journals. In some fields, significance testing has become the dominant and nearly exclusive form of statistical. P-value. In null hypothesis significance testing, the p-value, note 1, is the probability of obtaining test results at least as extreme as the result actually observed, under the assumption that the null hypothesis is correct. 2. 3. A very small p-value means that such an extreme observed outcome would be very unlikely under the null hypothesis. Even though reporting p-values of statistical tests is common practice in academic publications of many quantitative fields, misinterpretation and misuse of p-values is widespread and has been a major topic in mathematics and metascience. 4. 5. In 2016, the American Statistical Association (ASA) made a formal statement that p-values do not measure the probability that the studied hypothesis is true, or the probability that the data were produced by random chance alone, and that a p-value, or statistical significance, does not measure the size of an effect or the importance of a result, or evidence regarding a model or hypothesis. 6. That said, a 2019 task force by ASA has issued a statement on statistical significance and replicability, concluding with, p-values in significance tests, when properly applied and interpreted, increase the rigor of the conclusions drawn from data. 7. Basic concepts. In statistics, every conjecture concerning the unknown probability distribution of a collection of random variables representing the observed data in some study is called a statistical hypothesis. If we state one hypothesis only and the aim of the statistical test is to see whether this hypothesis is tenable, but not to investigate other specific hypotheses, then such a test is called a null hypothesis test. As our statistical hypothesis will, by definition, state some property of the distribution, the null hypothesis is the default hypothesis under which that property does not exist. The null hypothesis is typically that some parameter, such as a correlation or a difference between means, in the populations of interest is zero. Our hypothesis might specify the probability distribution of precisely, or it might only specify that it belongs to some class of distributions. Often, we reduce the data to a single numerical statistic, e.g., whose marginal probability distribution is closely connected to a main question of interest in the study. The p-value is used in the context of null hypothesis testing in order to quantify the statistical significance of a result, the result being the observed value of the chosen statistic. Note 2, the lower the p-value is, the lower the probability of getting that result if the null hypothesis were true. A result is said to be statistically significant if it allows us to reject the null hypothesis. All other things being equal, smaller p-values are taken as stronger evidence against the null hypothesis. Loosely speaking, rejection of the null hypothesis implies that there is sufficient evidence against it. As a particular example, if a null hypothesis states that a certain summary statistic follows the standard normal distribution, then the rejection of this null hypothesis could mean that I, the mean of is not 0, or E, the variance of is not 1, or E, is not normally distributed. Different tests of the same null hypothesis would be more or less sensitive to different alternatives. However, even if we do manage to reject the null hypothesis for all three alternatives, and even if we know that the distribution is normal and variance is 1, the null hypothesis test does not tell us which non-zero values of the mean are now most plausible. The more independent observations from the same probability distribution one has, the more accurate the test will be, and the higher the precision with which one will be able to determine the mean value and show that it is not equal to 0, but this will also increase the importance of evaluating the real-world or scientific relevance of this deviation. Definition and interpretation. Definition. The p-value is the probability under the null hypothesis of obtaining a real-valued test statistic at least as extreme as the one obtained. Consider an observed test statistic from unknown distribution. Then the p-value is what the prior probability would be of observing a test statistic value at least as extreme as if null hypothesis were true. That is, for a one-sided right-tail test statistic distribution. For a one-sided left-tail test statistic distribution. For a two-sided test statistic distribution. If the distribution of is symmetric about 0, then interpretations. The error that a practicing statistician would consider the more important to avoid, which is a subjective judgment, is called the error of the first kind. The first demand of the mathematical theory is to deduce such test criteria as would ensure that the probability of committing an error of the first kind would equal, or approximately equal, or not exceed, a preassigned number alpha, such as alpha equals 0.05 or 0.01, etc. This number is called the level of significance. Jerzy Neyman, The Emergence of Mathematical Statistics, 8. In a significance test, the null hypothesis is rejected if the p-value is less than or equal to a predefined threshold value, which is referred to as the alpha level or significance level. Is not derived from the data, but rather is set by the researcher before examining the data. Is commonly set to 0.05, though lower alpha levels are sometimes used. The 0.05 value, equivalent to 1/20th chances, was originally proposed by R. Fisher in 1925 in his famous book entitled Statistical Methods for Research Workers. 9. In 2018, a group of statisticians led by Daniel Benjamin proposed the adoption of the 0.005 value as standard value for statistical significance worldwide. 10. Different p-values based on independent sets of data can be combined, for instance using Fisher's combined probability test. Distribution. The p-value is a function of the chosen test statistic and is therefore a random variable. If the null hypothesis fixes the probability distribution of precisely e.g. where is the only parameter, and if that distribution is continuous, then when the null hypothesis is true, the p-value is uniformly distributed between 0 and 1. Regardless of the truth of the p-value is not fixed. If the same test is repeated independently with fresh data, one will typically obtain a different p-value in each iteration. Usually only a single p-value relating to a hypothesis is observed, so the p-value is interpreted by a significance test, and no effort is made to estimate the distribution it was drawn from. When a collection of p-values are available, e.g. when considering a group of studies on the same subject, the distribution of p-values is sometimes called a p-curve. 11. A p-curve can be used to assess the reliability of scientific literature, such as by detecting publication bias or p-hacking. 11. 12. Distribution for composite hypothesis. In parametric hypothesis testing problems, a simple or point hypothesis refers to a hypothesis where the parameter's value is assumed to be a single number. In contrast, in a composite hypothesis the parameter's value is given by a set of numbers. When the null hypothesis is composite or the distribution of the statistic is discrete, then when the null hypothesis is true, the probability of obtaining a p-value less than or equal to any number between 0 and 1 is still less than or equal to that number. In other words, it remains the case that very small values are relatively unlikely if the null hypothesis is true, and that a significance tested level is obtained by rejecting the null hypothesis if the p-value is less than or equal to 13.14. For example, when testing the null hypothesis that a distribution is normal with a mean less than or equal to 0 against the alternative that the mean is greater than 0, variance known, the null hypothesis does not specify the exact probability distribution of the appropriate test statistic. In this example, that would be the z-statistic belonging to the one-sided one-sample z-test. For each possible value of the theoretical mean, the z-test statistic has a different probability distribution. In these circumstances, the p-value is defined by taking the least favorable null hypothesis case, which is typically on the border between null and alternative. This definition ensures the complementarity of p-values and alpha levels, means one only rejects the null hypothesis if the p-value is less than or equal to, and the hypothesis test will indeed have a maximum type 1 error rate of. Usage. The p-value is widely used in statistical hypothesis testing, specifically in null hypothesis significance testing. In this method, before conducting the study, one first chooses a model, the null hypothesis, and the alpha level alpha, most commonly 0.05. After analyzing the data, if the p-value is less than alpha, that is taken to mean that the observed data is sufficiently inconsistent with the null hypothesis for the null hypothesis to be rejected. However, that does not prove that the null hypothesis is false. The p-value does not, in itself, establish probabilities of hypotheses. Rather, it is a tool for deciding whether to reject the null hypothesis. 15. Misuse. According to the ASA, there is widespread agreement that p-values are often misused and misinterpreted. 3. One practice that has been particularly criticized is accepting the alternative hypothesis for any p-value nominally less than 0.05 without other supporting evidence. Although p-values are helpful in assessing how incompatible the data are with a specified statistical model, contextual factors must also be considered, such as the design of a study, the quality of the measurements, the external evidence for the phenomenon under study, and the validity of assumptions that underlie the data analysis. 3. Another concern is that the p-value is often misunderstood as being the probability that the null hypothesis is true. 3.16. Some statisticians have proposed abandoning p-values and focusing more on other inferential statistics, 3, such as confidence intervals, 17, 18, likelihood ratios, 19, 20, or Bayes factors, 21, 22, 23, but there is heated debate on the feasibility of these alternatives. 24, 25, others have suggested to remove fixed significance thresholds and to interpret p-values as continuous indices of the strength of evidence against the null hypothesis. 26, 27, yet others suggested to report alongside p-values the prior probability of a real effect that would be required to obtain a false positive risk, i.e. the probability that there is no real effect below a pre-specified threshold, e.g. 5%. 28. That said, in 2019 a task force by ASA had convened to consider the use of statistical methods in scientific studies, specifically hypothesis tests and p-values, and their connection to replicability. 7. It states that different measures of uncertainty can complement one another. No single measure serves all purposes, citing p-value as one of these measures. They also stress that p-values can provide valuable information when considering the specific value as well as when compared to some threshold. In general, it stresses that p-values and significance tests, when properly applied and interpreted, increase the rigor of the conclusions drawn from data. Calculation. Usually, is a test statistic. A test statistic is the output of a scalar function of all the observations. This statistic provides a single number, such as a t-statistic or an f-statistic. As such, the test statistic follows a distribution determined by the function used to define that test statistic in the distribution of the input observational data. For the important case in which the data are hypothesized to be a random sample from a normal distribution, depending on the nature of the test statistic and the hypotheses of interest about its distribution, different null hypothesis tests have been developed. Some such tests are the z-test for hypotheses concerning the mean of a normal distribution with known variance, the t-test based on students' t-distribution of a suitable statistic for hypotheses concerning the mean of a normal distribution when the variance is unknown, the f-test based on the f-distribution of yet another statistic for hypotheses concerning the variance. For data of other nature, for instance, categorical discrete data, test statistics might be constructed whose null hypothesis distribution is based on normal approximations to appropriate statistics obtained by invoking the central limit theorem for large samples, as in the case of Pearson's chi-squared test. Thus computing a p-value requires a null hypothesis, a test statistic together with deciding whether the researcher is performing a one-tailed test or a two-tailed test, and data. Even though computing the test statistic on given data may be easy, computing the sampling distribution under the null hypothesis, and then computing its cumulative distribution function, CDF, is often a difficult problem. Today, this computation is done using statistical software, often via numeric methods rather than exact formulae, but, in the early and mid-20th century, this was instead done via tables of values, and one interpolated or extrapolated p-values from these discrete values. Rather than using a table of p-values, Fisher instead inverted the CDF, publishing a list of values of the test statistic for given fixed p-values. This corresponds to computing the quantile function inverse CDF. Example. Testing the fairness of a coin. As an example of a statistical test, an experiment is performed to determine whether a coin flip is fair, equal chance of landing heads or tails, or unfairly biased, one outcome being more likely than the other. Suppose that the experimental results show the coin turning up heads 14 times out of 20 total flips. The full data would be a sequence of 20 times the symbol H or T. The statistic on which one might focus could be the total number of heads. The null hypothesis is that the coin is fair, and coin tosses are independent of one another. If a right-tailed test is considered, which would be the case if one is actually interested in the possibility that the coin is biased towards falling heads, then the p-value of this result is the chance of a fair coin landing on heads at least 14 times out of 20 flips. That probability can be computed from binomial coefficients as. This probability is the p-value, considering only extreme results that favor heads. This is called a one-tailed test. However, one might be interested in deviations in either direction, favoring either heads or tails. The two-tailed p-value, which considers deviations favoring either heads or tails, may instead be calculated. As the binomial distribution is symmetrical for a fair coin, the two-sided p-value is simply twice the above calculated single-sided p-value. The two-sided p-value is 0.115. In the above example, null hypothesis H0, the coin is fair, with PR heads equals 0.5. Test statistic, number of heads. Alpha level designated threshold of significance 0.05. Observation O, 14 heads out of 20 flips. Two-tailed p-value of observation O given H0 equals 2 times min PR no. Of heads is greater than or equal to 14 heads PR no. Of heads is less than or equal to 14 heads equals 2 times min 0.058, 0.978 equals 2 times 0.058 equals 0.115. The PR no. Of heads is less than or equal to 14 heads equals 1 minus PR no. Of heads is greater than or equal to 14 heads plus PR no. Of head equals 14 equals 1 minus 0.058 plus 0.036 equals 0.978. However, the symmetry of this binomial distribution makes it an unnecessary computation to find the smaller of the two probabilities. Here, the calculated p-value exceeds 0.05, meaning that the data falls within the range of what would happen 95% of the time, if the coin were fair. Here, the calculated p-value exceeds 0.05, meaning that the data falls within the range of what would happen 95% of the time, if the coin were fair. Hence, the null hypothesis is not rejected at the 0.05 level. However, had one more head been obtained, the resulting p-value, two-tailed, would have been 0.0414, 4.14%, in which case the null hypothesis would be rejected at the 0.05 level. Optional stopping. The difference between the two meanings of extreme appear when we consider a sequential hypothesis testing, or optional stopping, for the fairness of the coin. In general, optional stopping changes how p-value is calculated. 2930. Suppose we design the experiment as follows: flip the coin twice. If both comes up heads or tails, end the experiment. Else, flip the coin 4 more times. This experiment has 7 types of outcomes: 2 heads, 2 tails, 5 heads 1 tail, 1 head 5 tails. We now calculate the p-value of the 3 heads 3 tails outcome. If we use the test statistic, then under the null hypothesis is exactly 1 for two-sided p-value, and exactly for one-sided left tail p-value, and same for one-sided right tail p-value. If we use the test statistic, then under the null hypothesis is exactly 1 for two-sided p-value, and exactly for one-sided left tail p-value, and same for one-sided right tail p-value. If we consider every outcome that has equal or lower probability than 3 heads 3 tails, as, at least as extreme, then the p-value is exactly. However, suppose we have planned to simply flip the coin 6 times no matter what happens, then the second definition of p-value would mean that the p-value of 3 heads 3 tails is exactly 1. Thus, the at least as extreme definition of p-value is deeply contextual and depends on what the experimenter planned to do even in situations that did not occur. History. John Arbuthnot, Pierre-Simon Laplace, Karl Pearson, Ronald Fisher. P-value computations date back to the 1700s, where they were computed for the human sex ratio at birth, and used to compute statistical significance compared to the null hypothesis of equal probability of male and female births. 31. John Arbuthnot studied this question in 1710, 32, 33, 34, 35, and examined birth records in London for each of the 82 years from 1629 to 1710. In every year, the number of males born in London exceeded the number of females. Considering more male or more female births is equally likely, the probability of the observed outcome is 1/282nd, or about 1 in 4 septillion 836 sextillion, in modern terms, the p-value. This is vanishingly small, leading Arbuthnot that this was not due to chance, but to divine providence, from whence it follows, that it is art, not chance, that governs. In modern terms, he rejected the null hypothesis of equally likely male and female births at the p equals 1/282nd significance level. This and other work by Arbuthnot is credited as the first use of significance tests, 36 the first example of reasoning about statistical significance, 37 and perhaps the first published report of a nonparametric test, 33 specifically the sign test, see details at sign test section history. The same question was later addressed by Pierre-Simon Laplace, who instead used a parametric test, modeling the number of male births with a binomial distribution, 38. In the 1770s Laplace considered the statistics of almost 500,000 births. The statistics showed an excess of boys compared to girls. He concluded by calculation of a p-value that the excess was a real, but unexplained, effect. The p-value was first formally introduced by Karl Pearson, in his Pearson's chi-squared test, 39 using the chi-squared distribution and notated as capital P. 39 The p-values for the chi-squared distribution, for various values of chi2 and degrees of freedom, now notated as p, were calculated in Elderton 1902, collected in Pearson 1914, pp. XXXIXXXIII, 26-28, Table 12. Ronald Fisher formalized and popularized the use of the p-value in statistics, 40-41, with it playing a central role in his approach to the subject. 42. In his highly influential book Statistical Methods for Research Workers, 1925, Fisher proposed the level p equals 0.05, or a 1 in 20 chance of being exceeded by chance, as a limit for statistical significance, and applied this to a normal distribution as a two-tailed test, thus yielding the rule of 2 standard deviations on a normal distribution for statistical significance. See 68-95-99.7 rule. 43. Note 3, 44. He then computed a table of values, similar to Elderton but, importantly, reversed the roles of chi2 and p. That is, rather than computing p for different values of chi2 and degrees of freedom n, he computed values of chi2 that yield specified p-values, specifically 0.99, 0.98, 0.95, 0, 90, 0.80, 0.70, 0.50, 0.30, 0.20, 0.10, 0.05, 0.02, and 0.01. 45 That allowed computed values of chi2 to be compared against cutoffs and encouraged the use of p-values, especially 0.05, 0.02, and 0.01, as cutoffs, instead of computing and reporting p-values themselves. The same type of tables were then compiled in Fisher and Yates 1938, which cemented the approach. 44. As an illustration of the application of p-values to the design and interpretation of experiments, in his following book The Design of Experiments 1935, Fisher presented the lady tasting tea experiment, 46, which is the archetypal example of the p-value. To evaluate a lady's claim that she, Muriel Bristol, could distinguish by taste how tea is prepared, first adding the milk to the cup, then the tea, or first tea, then milk, she was sequentially presented with 8 cups, 4 prepared one way, 4 prepared the other, and asked to determine the preparation of each cup, knowing that there were 4 of each. In that case, the null hypothesis was that she had no special ability, the test was Fisher's exact test, and the p-value was so Fisher was willing to reject the null hypothesis, consider the outcome highly unlikely to be due to chance if all were classified correctly. In the actual experiment, Bristol correctly classified all 8 cups. Fisher reiterated the p equals 0.05 threshold and explained its rationale, stating, 47. It is usual and convenient for experimenters to take 5% as a standard level of significance, in the sense that they are prepared to ignore all results which fail to reach this standard, and, by this means, to eliminate from further discussion the greater part of the fluctuations which chance causes have introduced into their experimental results. He also applies this threshold to the design of experiments, noting that had only 6 cups been presented, 3 of each, a perfect classification would have only yielded a p-value of which would not have met this level of significance. 47. Fisher also underlined the interpretation of p as the long-run proportion of values at least as extreme as the data, assuming the null hypothesis is true. In later editions, Fisher explicitly contrasted the use of the p-value for statistical inference in science with the Neyman-Pearson method, which he terms acceptance procedures. 48. Fisher emphasizes that while fixed levels such as 5%, 2%, and 1% are convenient, the exact p-value can be used, and the strength of evidence canon will be revised with further experimentation. In contrast, decision procedures require a clear-cut decision, yielding an irreversible action, and the procedure is based on costs of error, which, he argues, are inapplicable to scientific research. Related indices. The e-value can refer to 2 concepts, both of which are related to the p-value and both of which play a role in multiple testing. First, it corresponds to a generic, more robust alternative to the p-value that can deal with optional continuation of experiments. Second, it is also used to abbreviate expect value, which is the expected number of times that one expects to obtain a test statistic at least as extreme as the one that was actually observed if one assumes that the null hypothesis is true. 49. This expect value is the product of the number of tests and the p-value. The q-value is the analog of the p-value with respect to the positive false discovery rate. 50. It is used in multiple hypothesis testing to maintain statistical power while minimizing the false positive rate. 51. The probability of direction PD is the Bayesian numerical equivalent of the p-value. 52. It corresponds to the proportion of the posterior distribution that is of the median sign, typically varying between 50% and 100%, and representing the certainty with which an effect is positive or negative. Second-generation p-values extend the concept of p-values by not considering extremely small, practically irrelevant effect sizes as significant. Type 1 and Type 2 errors. In statistical hypothesis testing, a Type 1 error, or a false positive, is the rejection of the null hypothesis when it is actually true. A Type 2 error, or a false negative, is the failure to reject a null hypothesis that is actually false. 1. Type 1 error, an innocent person may be convicted. Type 2 error, a guilty person may be not convicted. Much of statistical theory revolves around the minimization of one or both of these errors, though the complete elimination of either is an impossibility if the outcome is not determined by a known, observable causal process. The knowledge of Type 1 errors and Type 2 errors is widely used in medical science, biometrics and computer science. Type 1 errors can be thought of as errors of commission, i.e., wrongly including a false case. For instance, consider testing patients for a virus infection. If when the patient is not infected with the virus, but the test shows that they do, this is considered a Type 1 error. By contrast, Type 2 errors are errors of omission, i.e., wrongly leaving out a true case. In the example above, if the patient is infected by the virus, but the test shows that they are not, that would be a Type 2 error. Definition. Statistical background. In statistical test theory, the notion of a statistical error is an integral part of hypothesis testing. The test goes about choosing about two competing propositions called null hypothesis, denoted by, and alternative hypothesis, denoted by. This is conceptually similar to the judgment in a court trial. The null hypothesis corresponds to the position of the defendant, just as he is presumed to be innocent until proven guilty, says the null hypothesis presumed to be true until the data provide convincing evidence against it. The alternative hypothesis corresponds to the position against the defendant. Specifically, the null hypothesis also involves the absence of a difference or the absence of an association. Thus, the null hypothesis can never be that there is a difference or an association. If the result of the test corresponds with reality, then a correct decision has been made. However, if the result of the test does not correspond with reality, then an error has occurred. There are two situations in which the decision is wrong. The null hypothesis may be true, whereas we reject. On the other hand, the alternative hypothesis may be true, whereas we do not reject. Two types of error are distinguished, Type 1 error and Type 2 error. 2. Type 1 error. The first kind of error is the mistaken rejection of a null hypothesis as the result of a test procedure. This kind of error is called a Type 1 error, false positive, and is sometimes called an error of the first kind. In terms of the courtroom example, a Type 1 error corresponds to convicting an innocent defendant. Type 2 error. The second kind of error is the mistaken failure to reject the null hypothesis as the result of a test procedure. This sort of error is called a Type 2 error, false negative, and is also referred to as an error of the second kind. In terms of the courtroom example, a Type 2 error corresponds to acquitting a criminal. 2. Crossover error rate. The crossover error rate, CER, is the point at which Type 1 errors and Type 2 errors are equal. A system with a lower CER value provides more accuracy than a system with a higher CER value. False positive and false negative. In terms of false positives and false negatives, a positive result corresponds to rejecting the null hypothesis, while a negative result corresponds to failing to reject the null hypothesis. Type 1 error. The first kind of error is the mistaken rejection of a null hypothesis as the result of a test procedure. This kind of error is called a Type 1 error, false positive, and is sometimes called an error of the first kind. In terms of the courtroom example, a Type 1 error corresponds to convicting an innocent defendant. Type 2 error. The second kind of error is the mistaken failure to reject the null hypothesis as the result of a test procedure. This sort of error is called a Type 2 error, false negative, and is also referred to as an error of the second kind. In terms of the courtroom example, a Type 2 error corresponds to acquitting a criminal. 2. Crossover error rate. The crossover error rate, CER, is the point at which Type 1 errors and Type 2 errors are equal. A system with a lower CER value provides more accuracy than a system with a higher CER value. False positive and false negative. In terms of false positives and false negatives, a positive result corresponds to rejecting the null hypothesis, while a negative result corresponds to failing to reject the null hypothesis. False means the conclusion drawn is incorrect. A system with a lower CER value provides more accuracy than a system with a higher CER value. False positive and false negative. In terms of false positives and false negatives, a positive result corresponds to rejecting the null hypothesis, while a negative result corresponds to failing to reject the null hypothesis. False means the conclusion drawn is incorrect. Thus, a Type 1 error is equivalent to a false positive, and a Type 2 error is equivalent to a false negative. Table of error types. Tabulated relations between truth, falseness of the null hypothesis and outcomes of the test. 3. Table of error types. Null hypothesis is true false. Decision. About null hypothesis not reject. Correct inference true negative. Probability equals. Type 2 error false negative probability equals. Reject. Type 1 error false positive probability equals correct inference true positive. Probability equals. Error rate. The results obtained from negative sample left curve overlap with the results obtained from positive samples right curve. By moving the result cutoff value vertical bar, the rate of false positives FP can be decreased at the cost of raising the number of false negatives FN, or vice versa. TP equals true positives, TPR equals true positive rate, FPR equals false positive rate, TN equals true negatives. A perfect test would have 0 false positives and 0 false negatives. However, statistical methods are probabilistic, and it cannot be known for certain whether statistical conclusions are correct. Whenever there is uncertainty, there is the possibility of making an error. Considering this, all statistical hypothesis tests have a probability of making type 1 and type 2 errors. 4. The type 1 error rate is the probability of rejecting the null hypothesis given that it is true. The test is designed to keep the type 1 error rate below a pre-specified bound called the significance level, usually denoted by the Greek letter alpha, and is also called the alpha level. Usually, the significance level is set to 0.055%, implying that it is acceptable to have a 5% probability of incorrectly rejecting the true null hypothesis. 5. The rate of the type 2 error is denoted by the Greek letter beta, and related to the power of a test, which equals 1 minus beta. These two types of error rates are traded off against each other. For any given sample set, the effort to reduce one type of error generally results in increasing the other type of